This is Introductory Nuclear Physics course, and we are discussing today radioactivity, and in this regard, the beta decay. I am Dr. Nasir Majid Mirza, and I will be talking about beta decay today in this lecture. First, let us talk about the properties of beta particles and how they are further classified. Beta rays are basically electrons that are either negatively charged or positively charged. These rays are made up of streams of negative charged particles or positively charged particles with a very small mass. They do affect the photographic plate. They get deflected to maximum extent towards the positive plate, and when electric field is applied. They are also deflected under the influence of magnetic field, and again, Lorentz force acts on them. Their ionizing power is less than that of the alpha particles. It is about 100 times smaller as compared to the alpha particles. Their velocities vary with the source and sometimes can reach to 2 to 3 times 10 to the power 8 meters per second. Very high speed they can attain. Their penetration power is about 100 times more as compared to alpha particles. Their mass is too small, and therefore they really can penetrate further deep. So they can be stopped by aluminum foils and other solid materials. Alpha particles can be stopped by a piece of paper. However, beta particles will penetrate further. Beta particles are capable of penetration through the skin. They have their penetration power larger as compared to the depth of the skin. Once we consider the beta process, it is such that A remains unchanged in a nucleus. A stands for the total number of nucleons. It means that that the total sum of the neutrons and the protons is constant, but n will change and z will change by plus minus 1. In beta minus decay, there are two types of beta decay. Beta minus decay is a decay in which the neutron breaks to a proton and an electron. And it is favored by the neutron-rich environment inside the valley of isotopes in periodic table, and beta minus is taking place when the isotopes are rich in the neutrons. If the isotopes are rich in protons, then the second process is favored. It is beta plus, where the proton-rich side of the valley favors that. A proton will decay to a neutron and the positively charged electron or a positron. The proton mass is in general small as compared to the mass of the neutron. However, this process is energetically possible because protons, if have large energies in the excited state, then that energy can get converted into the signatures of these neutrons and the positrons. Then there is a process of electron capture in which the proton captures an inner shell of the electron and becomes a neutron. We will further, these are the competing processes. But the simple example is a free electron, free neutron is allowed to sit, then that neutron will break into a proton and electron. It is about 10.8 minutes time in which, on the average, it will break or decay. So a nucleus which has A number and Z number goes to a nucleus of A and Z plus 1 with electron emission or a beta decay, and this is a kind of a beta decay for which the initial process was written. If we observe the experimental beta spectrum, by spectrum I mean to say that on y-axis we have the number in the form of intensity, in the form of flux, in the form of numbers of particles being emitted or observed, or a number of particles being observed in certain energy group, or number of particles being observed in certain time period for particular energy, and then you plot them on x-axis the energy of the particle or the wavelength of the particle or the frequency of the particle, then you get whatever curve you get is called a spectrum. Spectrum is a curve. On x-axis you get the energy, and y-axis you have the representation of the intensity. So experimental beta decay spectrum is like this. It is not with one energy. It has all possible energies up till E maximum, which is called endpoint energy. This all types of energies can get emitted in a beta decay. This kind of a spectrum shows that it is a continuous spectrum rather than a discrete or a single valued. Although the transition should be such that one energy should be emitted, but here we observe so many different energies. So assuming that it is indeed a two-body decay, we expect the energy and the momentum of the electron to be fixed. So the spectrum should have had a value or a certain small dispersion, what we call the full width at half maximum in the experiments. But the experimental spectrum shows a continuous variation for all possible energies up to E maximum, and it was not really in the scope of this equation that we could explain it. We needed further hypothesis. Pauli's neutrino hypothesis was proposed for this continuous variation of the kinetic energy of the beta particles. He said that such a spectrum spin is also needed to be interpreted. So he said that let me introduce another particle. So it is not a two-body reaction. It is a reaction in which a neutron breaks into a proton, an electron, and a neutrino. He proposed that all three particles in this reaction are the fermions. That is, they have the spin half. The proton has a spin half, the electron has a spin half, and the neutrino has a spin half. Spin of the proton and the electron can be coupled to 0 or 1 or -1. So the fermions must be present among the products so that the zero charge and the zero mass is there, but the spin is conserved. The angular momentum is conserved. This third body will take away whatever the energy is not given to the beta particle. So the total energy of the beta particle and the neutrino is constant. However, the share of the neutrino changes as the share of the beta particle changes. So beta particle gets a spectrum, a continuous spectrum due to this particle. The endpoint energy in the spectrum is the maximum energy that can be carried out by the beta particle with a minimum possible energy given to the neutrino. Every time the beta particle comes out with a different energy, there is a sharing of energy between the beta particle and the neutrino. The neutrino name means in a little neutral one, because it does not have any charge. It is a neutral, but it is a little neutral one with a very small mass or no mass at all. Experimentally, this was discovered in Cohen and Rhine's experimental work, and they showed that the inverse beta decay occurs, and therefore the neutrinos really are produced, and neutrino flux is there. And the reaction is true, and the Pauli's neutrino hypothesis is correct. If we consider today's ideas about the beta decay, they are like this. Here we see at the quark level, the down quark goes to up quark and the W particle. So here a down quark, this is a neutron. Neutron is composed of an up quark and two down quarks. And the beta decay is a process in which a down quark becomes up quark by this possible reaction in which the W particle and the up quark goes, and these two are coming independently out. So the up quark remains up and the down becomes like this, and you get a one down quark changing into the up quark makes it two up quarks and a down quark, and the thing is proton, and the beta decay is really manifested in this particular diagram where the W minus is the mediating particle between these, and the down quark transforms into the up quark, and the emission of the neutrino, antineutrino for the electron, and the electron are emitted. So the whole process is that a nucleus is converted into another nucleus, and you see the electron, the beta particle, and the antineutrino, the neutrino bar with the electron reaction is emitted. The energy consideration for the occurrence of the beta minus decay is really that the mass difference between the parent and the dot particle is converted to the kinetic energy of the dot particle, and the kinetic energy is the source of this reaction, which is coming from the differences of the masses. So we must concentrate on the nucleus, nuclear masses rather than atomic masses, because neutrinos are also massless. Therefore, we can neglect them in the equation, and we find the energy balance as mx minus my times c square in terms of the energy units. And if the Q value is positive, then we must have the mx larger than my to do this, and for beta decay to occur, the mass of the parent atom must be greater than that of the daughter atom, and such a reaction will take place. I have not gone through this, but you can satisfy yourself with the mass of the electrons, and they cancel out in the reactions, and we get the net answer in terms of the masses of the nuclear parent nucleus and the daughter nucleus. Let's solve one example. Neon 23 with Z is equal to 10 decays into sodium 23 with Z is equal to 11 by beta minus emission. And the question is to find the maximum kinetic energy of the emitted electron. The decay process is given by this equation. The total energy released is the mass of the neon minus the mass of the sodium times c square, and the differences are calculated, and the answer 931.5 is the conversion for the atomic mass unit into the energy using the E is equal to mc square, Einstein's energy mass relationship. The 4.375 is in million electron volts, the energy released in the reaction, and approximately the maximum kinetic energy of the electron is this Q, because the mass of the electron is very small as compared to the mass of the daughter nucleus. So majority of the energy will be given to the small thing, and it will carry almost all energy. This will occur for both anti-neutrino and the sodium, and they will the nucleus will get a very, very small amount of energy. Coming back to the beta decay, we have the positron emission from the unstable nucleus, which is based on this reaction, that the proton decays into a neutron and a beta plus and the neutrino. Or in terms of the isotopes, A and Z type is converted into A and Z minus 1 type by emitting a beta plus. The positron is a antiparticle of the ordinary electron, and it annihilates or get destroyed or get converted into the 2 photons of energy 0.511 million electron volts when it combines with the electron. These are called annihilation photons, and they are also signature of the positron. Wherever you get this energy 0.511 million electron volt energy photons coming, you can say that they are coming from the destruction of the positron with the electron. The transition energy must be larger than 1.022 MeV, which is needed before a beta plus can happen. So here is one study where we see the oxygen is getting beta plus decay and getting converted into nitrogen. Positron emitters are very useful in nuclear medicines because two photons that are generated per decay and coincidence techniques can be used to find out the signature of the positrons, and the topography can be done, and we can find very thin sheets and study the changes happening in the sheets of the skins or the tissues, and the positron topographic imaging is now very popular way of handling the finer details of tumors in cancerous parts of the tissues. As we know very well that X-rays and the other are the gamma rays are the hard rays, and they penetrate through the bones and the hard materials, but the tissues and the water retained bodies have a little or no effect at all, and they remain almost transparent to these radiations. But positron tomography gives the signatures and the correct view with the help of these inhalation radiations. Very commonly used positron emitters are the carbon, nitrogen, oxygen, and the phosphorus. Phosphorus 32 is also famous, and the PET machines are employing these isotopes. The Q value in radioactive decay can be further studied. Let us do this K40 study, which is an unusual isotope that it decays by a positive beta emission and then electron capture. Find the Q value for these two decays. When K40 undergoes a beta plus decay, it has a following reaction, and you can find out the mass difference and the mass of the electrons produced, and then you can convert them and find out the energy release. It is 0.482 million electron volts. However, when the electron capture is occurring, the K40 has the electron which is going into the K40 and converting it into argon 40 and a neutron plus the Q value of the reaction, and you convert it in the mass differences and find out that it has 1.5 million electron volt energy. Here 931.5 is the constant for the conversion of atomic mass unit into the energy. Now question is, can we have the electrons within the nucleus? If so, why don't the beta decaying happens? Why don't we see the beta particles within the nucleus staying there inside the nucleus? So let's check it out. Or how the beta particles are produced and they come out of the nucleus. Why can't they stay inside the nucleus? Heisenberg's uncertainty principle states that delta x in times delta p is greater or equal to h cut, which is h divided by 2 pi. Now take the delta x as the positional uncertainty, which is equal to nuclear dimensions, which means that the beta particle will be anywhere inside the nucleus. So delta x is of the order of 10 to the power minus 15 meters, which is 1 Fermi. The mass of the electron is 9.1 into 10 to the power minus 31. So this we can use for the figuring out the momentum. Now we have the momentum as m times delta v, the uncertainty in the velocity. So we can find out the uncertainty in velocity by substituting these values. Here, h Planck constant is 6.63 into 10 to the power minus 34 joules into second. And then the other values, 9.1 into 10 to the power minus 31 is the mass of the electron, and 10 to the power minus 15 is the distance, and we get the delta V of the order of 1.2 into 10 to the power 11 meters per second. We know very well that the velocity of light is about 3 into 10 to the power 8 meters per second. So this velocity, which is uncertain velocity, or the velocity one should see for the electron inside the nucleus, is far larger than the velocity of light. Therefore, it is a sheer violation of the special theory of relativity. Electron will not stay inside the nucleus. It will come out for the larger distances. And therefore, this velocity will be small. Now we know very well that the weak interactions are responsible for the beta decay. Professor Abdul Salam and Weinberg interpreted it further that the beta decay is due to the weak interaction, and weak interaction is really kind of sort of electromagnetic interaction at a different time and energy scale. So contrast to the decay of positron and the electron, which does not exist inside the nucleus, but are created in the decay. The atomic bonding is due to the force, which is electromagnetic force. So by what force? The nucleons are bound, a very strong nuclear force. We know that the electrons and the neutrinos are affected by the strong force. No, they are not affected. So the protons and the protons and the neutrons are affected. Yes, they are affected. Now, since the neutron is uncharged, the electromagnetic force does not affect it or affect to decay it. So how to explain the beta decay? We need a new form of force or indirection. Since beta decay lifetimes are much longer than the characteristic time scales in nucleus of the order of 10 to the power minus 23 seconds, this new force must be very weak as compared to the strong nuclear force. So that's how it was termed as a weak nuclear force. Modern notion of beta decay, if we look at the beta decay of a free neutron, then we can see these are the processes we can see. One up quark, two down quarks, one up quark, another down quark. This down quark getting converted into the up quark by this W minus mediating particle, the virtual W minus boson. and therefore the end product is a up quark and another up quark, and then a down quark, and then a W minus going away. So this kind of a behavior, we can see that the neutron with a down quark going to up quark and a virtual W boson, or a proton and a W minus boson separate, and an electron and an anti-neutrino are emitted, are created out of this virtual W minus boson. W minus is not independently staying as such. It gets converted into an electron and the anti-neutrino. The famous Feynman diagrams are also showing the same kind of result. Instead of doing this kind of a picture, we can have this time behavior in which up and two down, which is basically a neutron, is getting converted into a proton, which is up and down, and then up. One down was converted into up. As it was getting converted, it gave away the virtual W minus boson, and W minus broke into these two parts, the antineutrino for electron and an electron. These both were emitted, and their masses and the virtual behavior can be studied, and the differences can be studied, the mean lifetime can be studied, and this is the current trend of understanding the weak force and the beta decay. If you look at the isomeric transitions, IT, and the internal conversion, I see the daughter nucleus of the parent isotope can have a long life state or a meta-stable state. It is called the isomeric state, as opposed to the excited state. So decay of a meta-stable state into a stable state by emission of a gamma ray is termed as isomeric transition. Such a metastable nucleus can also decay by transferring the energy to orbital electron, and that kind of behavior is called internal conversion. So once it is in excited state can be a little bit longer than it is isomeric state, and if it decays by ejection and meta-stable nucleus decays by transferring energy to the electron, orbiting electron, then it is internal conversion, and the electron ejected is an internal conversion electron. But it is just like a beta minus decay, but the difference only is that the beta decay electrons are coming from the nucleus, whereas IC electrons are coming from the electrons that are orbiting around the nucleus. Beta minus decay has shown the continuous energy spectrum, and IC electrons have a discrete energy spectrum. The famous technetium-99 with M, the metastable state, or written as 99M technetium, is a metastable popular radionuclide, which is used as a nuclear medicine imaging isotope. It is to label and tell us about the image of heart, image of lungs, image of various parts of the body. Technetium-99, which is a metastable isotope, is employed. Let's very briefly talk about the electron capture. In a neutron deficient nuclei, a proton can get converted into a neutron. So a positron and antiparticle of electron is emitted, and the electron and the neutrino will be coming out, and for a beta plus decay, this kind of a reaction will happen. where too we know very well that it will be possible if the mass of the parent is large as compared to the mass of the daughter. The electron capture as a computation to beta plus is a process in which the proton more favorably get converted into a neutron by absorbing an electron and emit a neutron. The K-shell electrons have the high probability inside the nucleus that they can easily be captured and then make this kind of conversion. Again, the mass of the parent element must be large as compared to the daughter. The excitation energy must be made available. There is another effect which I have shown here very briefly, Auger effect. It is an alternate process to the X-rays emission. When a hole is filled with a strong bound electron shell, then such a effect comes out, and we know very well that transition occurs when electron moves from one energy level to another. You can have the characteristic X-rays, but Auger is a process in which the hole is filled by the electron. Here I have tried to show the energy levels for the molybdenum and technetium. We make a molybdenum isotope in accelerator, and we attach it to the compatible molecules and then inject into a patient to observe that the patient is emitting gamma rays. And usually patients do not eat the detector, as the gamma ray penetration is high in the body, and you can have the substance as a tracer. The molybdenum is an isotope which emits the beta particles. So this line is indicating the beta and technetium in the excited state, and this technetium then decays with a certain life, 6.01 hours, and the molybdenum stays has a life of about 66 hours, and therefore can be very useful. We can investigate and study the effect of technetium-99 and the emitted beta particles or the gamma rays coming out, and study the various paths of the tracer, and we can also study how this is getting separated in a place with the tissues and the bones, and both are basically for the beta decay that leaves the signature, and can be used very useful for the nuclear medicine and for the medical physics studies. Beta particles and the beta decay is very effective in telling us a story about the nuclear forces that were really combined together. And we now very well know that Professor Abdul Salam has developed the correct version of converting this force, the weak nuclear force, into electromagnetic at high temperatures. And he told us that they are really all manifestation of a single force. And beta decay is showing its signature with the help of these W particles, the W minus, the W plus, and Z particle. And now we know very well that such a behavior is possible for the other forces as well. We stop here and we will move further to the gamma rays, the ideas about the gamma rays in the radioactive materials in the next lecture. Thank you so much.